All right, hello everyone. Really appreciate the opportunity to speak about some of our work on this project. And just before I jump into this very far, I just really wanted to acknowledge the lead author on this body of work, Dr. Jimmy Larson, who's now assistant professor at Utah State University, working in the field of pomology. Really excited that he's not only a key contributor here, but a product of this project, and couldn't be prouder of him in that endeavor. So I'm going to talk about a little bit of a different approach to try to estimate uh, chemical thinner efficacy, and I'll describe a little bit of our trajectory here throughout the course of this project. So we really wondered if there was any potential to develop technologies where we could get an earlier or more accurate estimate of fruit abscission. And to do this, we just kind of looked back at the literature to see if there were any factors that maybe hadn't been evaluated recently, and came across this nice paper by Dan Ward and Rich Marini in 1999, where they identified a few potential factors whenever they compared populations of fruit that received chemical thinner as compared to a population of fruit that didn't. And they felt like fruit stem water potential, starch concentration, and dry matter content of those fruitlets might play a role here. So you fast forward to the year 2020, there was an Israeli research group led by Orlova et al. That had begun to evaluate the use of visible or near infrared spectroscopy. And that sounds like complicated technology, but ultimately, this type of equipment shoots a beam of light at a specific target, and then in many cases, it'll capture the light that reflects off of that target. And based off of that data, you can get some really interesting information. And they were able to demonstrate that with 80% accuracy that they could determine abscission prediction whenever they used this 6 days after a thinner was applied. And they felt pretty strongly. If you look really closely at the picture on the right of the screen, you can see that little bit of fuzz on the fruit surface. So those are trichomes, and they felt like the density of these trichomes might be leading to this difference in spectral reflectance and might be able to be used as a potential indicator of fruit abscission potential. So we picked up this work and used an off-the-shelf handheld portable spectrometer, the Felix F750, which is used in many cases for a very different application. In a lot of instances, you can utilize this instrument closer to harvest to estimate sugar content or dry matter content once you've developed a model with that. So we wanted to see if we were able to shoot that light at individual fruitlets within a cluster, capture that reflectance spectra on the way back, to see if we could be able to estimate if fruit were going to be able to abscise or persist, and have these non-destructive assessments. And we were very keen to understand, could we get an earlier prediction with this technology? So this is a picture of Jimmy on the right here, and he had two very core areas of focus throughout his dissertation and also postdoctoral program with me. Was first to build a model using the equipment I've just described there to see if we could estimate chemical thinner efficacy, and then also to understand some of the why behind that question, which is what are the key characteristics of persisting and abscising fruitlets. So, and I'm going to show you a list of studies that were done throughout the course of this project here shortly, but at the crux of all of them is a very simple set of methods, which we tagged 100 spurs per orchard block that we were interested in, which was 20 spurs on 5 trees. Then we went through with the Felix on a regular interval at a day before thinner application, 3 days after, and 6 days after thinner application. And in general, we targeted the typical post-bloom thinning window, which is that 8 to 12 millimeter diameter for your fruit size. And then we just followed up at the end of June drop to get an estimate of how many fruit persisted, how many fell off, and to be able to understand how our model performed. So throughout the course of this project, there were 10 different orchard sites that were utilized across 3 states. So we had sites in North Carolina, New York, and Michigan throughout the course of this project. The top 8 locations ultimately are what we utilized to build our model, and the bottom 2 in green are what we used as external validation steps. And I'll show that data here as we go throughout this presentation. I do want to note that we looked at, it was a total of 3 states, 5 different cultivars, and then we looked at a number of post-bloom thinning chemistries that would be used typically at that 8 to 12 millimeter stage. So what we were trying to understand is, did we need one model to estimate, fruit abscission? Or did we have to have cultivar-specific models, or even thinning chemistry or location-specific models? We wanted to understand if it was a one-size-fits-all approach or not. And as part of this too, what we wanted to accomplish was to have a nice wide range of fruit set potentials that occurred across these locations. So it's notable in these studies that we had between 15 to 84% fruit set. So there were some years that we had nice thinning responses, other years not so much. And that sounds very accurate probably for anybody who's tried to thin a crop of apples chemically before. But we were really happy with that range. Obviously, more data is better in these cases, but we were excited to see that we had a nice range throughout the development of this model. This figure that I'm showing you here is just from 1 year in one location. So this is a Honeycrisp trial that we did in 2021, kind of our proof of concept trial. And this is representative of the scans that we took with that Felix instrument at 3 days after the thinner application. And what you're able to see is that this instrument on the x-axis here on the bottom of this figure, that just shows you the wavelength of light that was ultimately captured by the instrument through the detector. And then on the y-axis is the reflectance, or the intensity of that reflectance that occurred. And what's really interesting is that between 400 and 700 nanometers, you can see that there's a lot of situations where we have clear separation between fruit that are going to persist in blue and fruit that are going to fall off, which are in red. The other area that we see separation in these scans would be right there around 1,000 nanometers, just a little bit below that. And what's interesting about that specific interval or area is that it's thought that really corresponds well with water content of structures by people do work in this area. And then at 400 to 700 would align a lot more with pigments. So we kind of had some nice leads on what we were detecting with this instrument. But it's notable that we saw these shifts within 3 days after the thinner application. And what I'm going to show you throughout the rest of this presentation, we took measurements after this, but I'm only going to show you the data and the model performance with that 3 days after the thinner application, because I really think that if a new technology is developed in this area, it has to have an advantage because there are other models, as Todd just described, and other technologies that can predict really well once you get to 7, 8, 10 days after the thinner application. And usually by 2 weeks, you can see it with your eyeballs. So we need to have a gain in not only accuracy, but I would also say that early detection time. It's notable that if you decide, oh, I want to buy one of these instruments and use it, it's not an off-the-shelf thing. You have to collect the data set, then through a series of statistical and modeling techniques, you have to balance your responses, normalize the data, and then build a model, which is what we did. So this is not off the shelf. This is not ready to go for a grower, but our hope was to have a proof of concept here across the course of the project. And overall, across those 10 or those 8 sites that I showed you there, we had it was 77% accuracy to overall model performance. And whenever you look at the specific aspects of the model, whether it was accurate in predicting fruit that were going to persist or abscise, you'll note that we had a very balanced model. It wasn't like one of those 2 categories. We saw consistent over or under prediction, and I'll show you that in the upcoming figures as well in a different format. So this dash line that runs up and down on this figure here, that shows the full model performance, and each one of these orange dots corresponds with a different data set of those 8 that were used to build the model. So you can see that most of these, we were very consistent with the overall accuracy of the model. And what's interesting when you look at the accuracy of those categories of predicting abscission or predicting persistence, there's no consistent trends that were consistently over or under predicting abscission across this. So we were pretty pleased overall with that, but there's a really good question of, is 77% accuracy good enough? And that's something I'd like to circle back to at the end here. Whenever we showed or we put data in front of this model that it hadn't seen before, we did this in 2 different ways. We did that first with a Gala trial in 2023, where 10 parts per million NAA was applied. And ultimately, the actual fruit set was 30%, and our predicted fruit set percentage based on our model was 36. So that was really nice agreement there. But there was a different case where we took some data out of New York, and it didn't align very well, and I'll show that next. So in 2022, with a Honeycrisp data set, ultimately the actual fruit set was 11%, but the predicted fruit set was 36. But what's really notable here, as you'll recall, our original model, the range of fruit set that we've observed with that model and that model was built on, only went down to 15% fruit set. So ultimately what happened here is that this data that we introduced to the model was outside of the range of that existing model. So that's why we hypothesized that it performed quite poorly, and it seemed to do a really bad job. It was almost as effective as the coin flip is whenever you were predicting if a fruit was going to upsize or not in this case. So this by no means is a perfect ironclad technology because we don't have robust enough data quite to this point. But I do want to acknowledge what we're detecting with this instrument, since I mentioned that previously. Ultimately, we did some really nice work looking at indices with both plant water content and chlorophyll, and saw that we were able to really see separation with that 3 days after treatment as it relates to total chlorophyll of structures, which would be somewhat aligned with fruit size, along with that water content of different structures, and we've published that data. We were also very curious about the trichome feature of this, and that was published in a separate paper. But ultimately, we denuded some fruitlets with using Scotch tape to remove all that pubescence there, and then we scanned the fruit with pubescence and without, and ultimately that had no significant impact on our prediction values there. So just to summarize this quickly, that combined model or that omnibus model was relatively consistent across locations, cultivars, and the three thinning chemistries that we evaluated. I do question if 77% model accuracy is acceptable. It's very rare whenever you look at other models that are out there, like what is their accuracy truly? It's either, we make a lot of generalizations here, but there are some calculations on understanding if the model is consistent or not. And I'll acknowledge that we did have cases with that New York data set in particular, when we had very low fruit set that was outside of our model range. And the way to correct for that is to include more data in this model moving forward. I feel pretty strongly that total chlorophyll and fruit water content of fruitlets are important predictors that could be used in this technology or in others in the future to try to predict fruit abscission. And again, you've got some really nice tools at your disposal, as Todd just described very well. That size distribution model is a great tool, and it's ready now, along with some of the tools that are being developed by some of the ag tech companies as well. So I will say that if this is to ever take off, we need to find a way to scale up this process and technology for early accurate predictions of apple fruit abscission. And very briefly, I just want to acknowledge we had a lot of grower cooperators that were involved in hosting us in this project, both here in North Carolina and beyond, and some great teams across all three locations that participated. So thanks to everyone for their participation and support. So thank you.
Thanks, Tom. Questions? Craig, do we have questions?
Yep, there's a couple in here. Can fruitlet size measurements from vision systems be used to predict fruit abscission?
Rod, I believe we've done a little bit of work with this in some cases, but the fruitlet size measurements, I believe, as I understand it, in most of these systems, and I would encourage Terrence or others to jump in here because they've done more work in this area, but indeed those estimates of fruit size from a vision system are being used by some models and systems, and Todd presented on that as well.
Let me comment on that question.
Sure.
We had, I thought, very, very good results with the Palmetto cell phone video system, where you take a video of certain trees and then repeat it a few days later, and they measure the differences in fruit size, and we got very accurate estimates of fruit abscission. But Palmetto has withdrawn from this space, and that model is not available. When other companies we have tested with, like Todd has done, the Vivid system, it has had some challenges that we don't feel comfortable yet with that model of estimating fruit abscission. Would you comment further on the Vivid experience?
Yeah, I agree, Terrence. I think one of the limitations or issues with that is that there is a lot of calibration that needs to be done when using that system, so much that it requires an exorbitant amount of time. And it seems like for an automated system, you would be avoiding all of that, but it was really necessary. The second issue was not in their accuracy and prediction, because it was pretty well aligned with what we came up with our model and what we quantified at harvest and when final fruit set was. The issue was that if you wanted to do something like variable rate, it could not seem to find the exact tree and put a number of fruit to an exact tree down the row. And that really limited us in some variable rate experiments that we had designed when we needed to know the exact number of fruitlets on a given tree. I suspect that can get all worked out. It's all geo-referenced, but tree 41 is not tree 40, and that throws everything off. So, that's a small but really important limiting factor. That was my experience, Terrence.
A few questions in here. One, are the spectroscopy results affected by ambient light conditions?
They can be, absolutely. And ultimately, the spectrometer that we utilized has a small cone that would go around the entirety of the fruit to try to improve the consistency of those light conditions. And the problem with that is the cone is only so large, the detector is only so large. We're doing individual fruit at a time. There's a lot of limitations in what we utilize for this, but certainly ambient light can be influential, but we tried to manage that with a simple but effective technology, which is a metal cone that wraps around the fruit.
What would be the next steps for commercializing the spectroscopy method?
Oh, that's a really good question. I think that, ultimately, I feel like we're still learning a lot about this and still need to get more data to make sure that we have a really robust model before we can move forward with this. I think that's probably step one. I think that, ultimately finding whether it's an ag engineering team or commercial partner to work with to see if we can do this at a scale that isn't individual fruitlet. So I'm currently working with some ag engineering and computer engineering colleagues at NC State University to try to expand the scale of this right now, but it's in its very early stages. So I still feel like there's long ways to go with this, and there's better answers right now, but thank you.
Thanks. There's one quick one before I think we run out of time. Do fruitlets need to be dry to predict in 1,000 nanometer water spectral region?
Rachel, that's a great question. And all of our fruit that we evaluated we made a point that they were dry, at least at our sites here, before we used anything. And I would expect that that could be influential, but I don't know that for sure. And I would probably need to defer to my colleague Jimmy, who led a lot of this work. So.
Thank you.